Hello and welcome to Chandler Science AP Physics 1 Simple Harmonic Motion. In today's lesson we're going to talk about harmonic motion. What is it? How you calculate the period, the frequencies, some of the forces acting on these objects, and we'll do some problems at the end, some examples to help us clarify any confusion we may have about this topic. So without any further introduction, let's get started. From my classes, this is a special kind of COVID-19 episode of this Chandler Science here. So you're not doing the discussion, but you'll be answering some book problems at the end of the video, and you'll be doing some practice of our cues as well for your grades. So be on the lookout for those on Schoology. If you're from somewhere else on the internet, welcome. Hope you enjoy, and hope this helps you out with SHM, or Simple Harmonic Motion. So let's get started. All right, so what is simple harmonic motion? What does that term even mean? Let's talk about the definition before we go any further. Periodic motion. Let's see, simple harmonic motion definition is periodic motion, and that just means periodic means motion that repeats over and over, right? So it cycles, right? It does a motion and does it again and then again, right? So it's periodic. Another word you might hear is oscillator, which we see down here, and we'll do that in a minute. Or you might say harmonic, right? All those kind of terms mean the same thing. Harmonic, periodic, or oscillation, all kind of the same thing. It repeats. All right, so simple harmonic motion is periodic motion where an object's restoring force is proportional and opposite to the object's displacement from equilibrium. All right, so kind of a mouthful. We'll dive more into that in a minute here. Before we look at the definite or those different terms, I want to talk about some labs that we would have done if we weren't on quarantine at home. And it's going to kind of help us with this definition of restoring force. So there are two labs we usually do. One with the pendulum and one with the spring oscillator. We kind of combine them into one big lab. For the pendulum, what we do is take a pendulum like this. And a pendulum, if you don't know, is just an object that's hanging from a string, right? And if you let it go by itself, this is where it wants to hang. This is where it wants to be, right? It wants to be at its equilibrium position. And what we do is we take this object and kind of lift it up to where it's here, maybe, and we let it go. Very exciting lab. And we let it go, and it would go down here, and back up to here, and then it would go back, right? And back up to its original position. And what we would do is we would time how long it takes for it to go down and back. But we would vary some things. I would have some groups vary the length of the string. I would have some groups vary the mass hanging on the end of the pendulum. And some groups vary the angle theta from which they lift up the pendulum, right? Maybe some really high, and they would vary those things, right? So one group would vary the length of string, real long string, real short string, but keep the other things the same. One group would vary the mass on the end of the pendulum, but keep the other two the same. And then the third group would vary the mass of theta, but keep the other two the same, right? So we know we're testing. All right, so I want you to think to yourself for a minute, before we get into the whole what's the restoring force and all of this stuff, which of these three things, and it could be more than one, or it could be none, or two out of the three, which of these three properties here, the length of string, the mass on the end of the pendulum, or the angle theta with which we lift the string, which one of those three, or multiple of the three, affect how long it takes for the pendulum to swing down and then back, right? And if you want to be real extra, you think, okay, well, if you think that like the theta, the angle matters, then does a bigger angle mean more time or less time for it to go down and back? Okay. Now, for a spring oscillator, the lab we would do is very similar. We take a spring oscillator. All that means is that spring oscillator system is usually we have a spring attached to like a wall like that, right here on the wall. And here's the spring, and then here's the object. And remember, this would be our equilibrium position, where the spring wants to be when it's at rest. And we would do is we stretch it out, right? Maybe to this far. This would be a distance d. Stretch it out all the way out to here, maybe. And let it go, and then the spring would go oscillate back and forth motion, and we would time how long it takes for the spring to go down and then back. How long does it take for one cycle, right? Down and back. How long does that take? One period. And again, there are things we can vary, right? So I would have some groups vary the distance d with which that they displace the object from equilibrium. Some groups would vary the mass of the object, and then some groups would vary k, the spring constant of the spring. And again, same thing. Which one of these three do you think matter? Or maybe it's two out of three, maybe it's all three, or maybe it's none of them. Which one do you think make a difference? Remember, spring constant means how strong the spring is. High spring constant means really hard spring. D, the distance from the equilibrium position, or M, the mass of the object attached to the spring. Which one of those three things or again, combination of the three, do you think would affect how long it takes the spring to oscillate back and forth, how long it takes for one period? All right, so pause the video, ask yourself that question, imagine it in your head. You can't really do it. You can try and get, if you have, all you need is a string. I'm looking around for a string. All you need is like a string and tie a ball or whatever you want to the end of it, and kind of do a little quick experiment with yourself at home if you want to, and kind of test your own theory for a minute. So pause the video, think about it for a minute, and then go to the next slide. All right. So did you make your predictions about which of those three, or a combination of the three parameters, sort of affect the period of a pendulum? All right, hopefully you did. So let's go ahead and take a look and see which of those things actually matter. All right, so what are the forces on a pendulum? We mentioned that term restorative force a second ago, and maybe you were wondering, wait, what's a restorative force? I've never heard of that before. I know about weight force and friction force and tension force and applied forces, but what's a restorative force? Some new kind of force? No, in fact, it's just for a pendulum, it's just gravity, really. But the restorative force is a special term we use to describe the force that is the force responsible, so to speak, for returning the object towards equilibrium position. So let's take a look at our pendulum. So here we go. So here's a pendulum. Equilibrium position will be here, say, object hanging vertically down, and then we pick the object up and we raise it up to, say, I don't know, yay high. And let's draw our free body diagram for the object at that new position. So we're going to have the weight down, right? Weight force is straight down like this, mg. And we're going to have tension force up the rope, right? Like so. Now, the moment I let go, right? So I remove my force in my hand from it. Those are the only two forces on the object. Now, which direction is the object going to go? Well, if you think about this for a minute, you should be able to know, well, you know what direction it's going to move. You're going to go kind of down to the left, right? Is that left on your screen? Yeah, I think so. It's going to go this way, right? So you know that the net force must be that direction, because that's the way it's going to accelerate. And net force and acceleration always go together. So what is it? No, my circle. What is a net force? There we go. All right, so if you think about it in terms of vectors, tail to tip, we have the weight force going straight down, and then the tension force going up like this. But if we draw them tail to tip, weight force is down like this, tension force is up this way, tail to tip means, oh, look at that, we have the net force going kind of down and left, right? Which is what we expect. Another way that you can think about this, if that doesn't quite make sense to you, is to think, well, the weight force is going to have components, a component down this way, and then a component down this way, right? Now, the tension force and this component of the weight force are going to cancel out, right? They're going to kind of nullify each other because they're opposite but equal directions, which leaves only this component of the weight force to actually do anything. But look at what direction that weight force is in, right? It's in this direction, which is towards equilibrium position. So that is the restoring force in this case, right? Now I want you to think, all right, well, as we get closer to the equilibrium position here, does that restoring force get bigger or smaller? All right, so make a prediction in your head real quick, and we'll do it. We'll see. So now I'm real close to equilibrium. I'm right here, right? So now I have weight force. Weight force is the same, still down, mg. Does the tension force get larger or smaller as we get more vertical? It's bigger, a little bit bigger. So tension force is there. Now we have, again, the weight component down this way, and then a little bit smaller, kind of, horizontal or perpendicular component there. This force and this one will cancel. All right, they nullify each other out, equal and opposite, which leaves only this tiny little component of the weight force to go down this way, which means that actually, so as the angle gets smaller, so does the restorative force, right? Which again kind of makes sense, right? Remember, go back to our other definition, or the only definition we have of harmonic motion, the periodic motion where an object's restoring force is proportional and opposite to the object's displacement. Well, displacement from what? From equilibrium position, right? So as displacement gets smaller, right? We're only this far now. I mean, it's just getting kind of busy in here. Let me get rid of some of this stuff. As displacement gets smaller from equilibrium, right? The force also gets smaller. And when we were way out here, the displacement was very large, but the force is also larger, right? So displacement got bigger, so does the force. Makes sense. And not only that, they're in opposite directions, right? The displacement is to the up and to the right, and the force, the restorative force is down and to the left, which makes sense, right? So there we go. There's our forces. So what do you think about our lab then? Now, after looking at this, you might think, oh, well, if the force does get larger, when the angle gets bigger, maybe the length of string or the angle does matter. But you would be wrong. It turns out we had three options, right? There was a theta angle, mass on the end of the pendulum, and an L length of string. Well, it turns out that the only one that actually matters out of these three is L. M doesn't matter, and theta does not matter. Why doesn't M matter? Think about it for a minute, guys. M. Does it matter what the mass is? Don't all objects fall at the same rate? 9.8 meters per second squared. The acceleration of any object is the same. If you took a pendulum and you hung a piano from the end of it and then you let it go and you did the same experiment with the same string, the same rope, and everything was the same, but you attached like a dime to the end of that string and let it go, it would have the same period of motion as the piano did, in theory anyway, because there's tension for it, or friction and stuff going on, but it would change that. But in theory, it would be the same. All right, so this leads us to we talk about the period now of pendulums. So I'm going to give you a formula. The period of a pendulum, and I put a little P here for pendulum. You'll see this on your formula sheets during your AP exam or formula sheets there. P for pendulum, capital T for period. And as a quick recap, capital T, which is period, is how long how long an object takes. My handwriting has gotten much better since the virus. Just kidding. How long an object takes to complete one cycle, right? Cycle means down and back, right? Down and back. All right, so the period of motion is, for a pendulum now, is 2 pi times the square root of L over G, where G is the acceleration of gravity, so on Earth, 10, right? And L is the length of the string. That's the only thing that matters, right? That's it. You can change the mass. You could even change the angle. Now, some of you might be wondering, because typically in class students do wonder this, why doesn't the angle matter, right? Doesn't it make sense that if I go up a further distance, the object has farther to travel? So if it has further to go, shouldn't it take longer to go a further distance? And at first you might think, yeah, it kind of makes sense, but then you got to realize, but wait a second, when you go further up, when our displacement gets further from equilibrium, the force also gets larger. And if the force gets larger, the acceleration gets larger. So you let go of an object way up here, it accelerates faster down, and so it covers more ground, but it's accelerating more, so it will cover that ground a little quicker. And again, I invite you to try this at home. Take an object and attach it to a string. I should have prepared better. I'll go grab one in a second, and I'll do it in the next little clip here. And take it out this high, let it go, down and back, kind of count off in your head if you want to, and then go way up higher, let it go, and I promise you, it will be the same, and I'll show you here in a second with an actual pendulum. All right, so that's restorative forces on pendulums. There's our formula. And we can also do frequency. Now remember, frequency, quick recap, frequency for a pendulum is the opposite, right? Remember that period is 1 over F, and F is 1 over period. So what was frequency? What does it mean? Frequency is how many cycles erase. How many cycles an object completes per unit of time, usually in 1 second, but it doesn't have to be a second. Right? So usually it's like how many cycles per second, but it doesn't have to be, right? It can be RPMs, and RPMs, revolutions per minute. So that's frequency based on minute instead of seconds, but you get the idea. So frequency, if frequency is 1 over t, and this is t, then we're going to do 1 over all this, right? So frequency will be 1 over 2 pi times the square root of g over L, right? We just flip them over, right? Do the reverse. So there you go. So there's a couple formulas. I'm pretty sure that this one is on your formula sheets. I don't know about this frequency one, but again, if you know one, you kind of know the other one, right? So, all right, cool. Let's go to the next slide, and I'll grab a pendulum real quick. I'll pause the video. I'll come back with a pendulum. I'll show you how that actually turns out to be true. All right, next we'll do oscillators. Awesome. All right, I got a pendulum. It's the best I can do. It's a mouse, but whatever, it doesn't matter, right? It's a string and an object hanging on the end of it. And I'm going to take this object, and let's just kind of, we'll count it off real quick. So I move about yay high, and I'll let go. It's kind of how long it takes to go down and then back, right? So 1 Mississippi. So about 1 Mississippi, right? Now if I take, give or take, a little bit higher, like almost off screen here, like do the exact same thing, 1 Mississippi. Back of my hand at the same time. You see how much faster it moves when I move it higher up? Because the restorative force is larger, right? It's a lot quicker. If I go way down here, remember this is equilibrium position, so just off to the side a little bit, it goes real slow, right? Up here, boom, real fast. Down and back, much quicker. But it has further to travel, so it ends up not making any difference. If I change the length of the string, maybe I make the length of the string really small. Like maybe just this long, you'll see that, now I'll make a prediction. Remember the formula for harmonic motion. The period is 2 pi times the square root of L over G. And I just realized that I wrote, my picture was on top of the definition of frequency, but hopefully you're able to still get that. Anyway, all right, if the L is in the numerator, if L goes down and gets smaller, right? I made the L real short now, right? As opposed to being longer. So L is smaller. Well, should the period, how long it takes for the object to go down and back, be longer or larger or smaller, right? So L is going down. Does the period also go down or does it get bigger? All right, let's see. So make it real short. 1 Mississippi. I can't even finish saying 1 Mississippi. So I think as L goes down, so does the period, right? Which makes sense because they're both in the numerator. So if L goes down, so does the period. Now it's not directly related, right? Because L is under a radical, but they go in the same direction. So if L gets smaller, so does the period. Okay. So real quick, this slide will just take a second. I just went to like one quick problem with you over this kind of thing. So we know the period of a pendulum is 2 pi times the square root of L over G. So if I have a pendulum, whoa, what is that? A pendulum whose L, let's say, is, I don't know, maybe it's 20 centimeters. And I hang a mass on the end of it, and the mass M is 2 kilograms. And I put it up, had it here at an angle theta of 20 degrees. How long is it going to take for the object to go down and back? Well, again, I gave you a bunch of information there, and we're on Earth, okay? So the period of the pendulum is 2 pi square root of L over G. I gave you all this information about the mass and the theta. They don't matter, and you'll see that on the AP exam. They'll give you stuff like that. It's just extra stuff. You don't actually need it, right? All that matters is the length of string L, 20 centimeters. Let's convert that to meters. It'd be 0.2 meters, right? So period of the pendulum is 2 pi times the square root of 0.2, and converting that to meters, over 10, that's G of course, and we just do the math. So pretty straightforward, nothing too crazy complicated about it. 0.2 divided by 10, of course, is 0.02, and the square root of that will be 0.14. So the period of pendulum is 2 pi times 0.14. So 0.14 times 2 pi, and I am getting about 0.9 seconds. So period of pendulum P, 0.9 seconds. And you do want to have your L in meters, not centimeters. So you want to convert that. And you want to have your G, of course, is, in meters per second squared. So make sure your units line up. Otherwise, pretty straightforward. All right. Okay, cool. Let's go to the next part here. Force on a spring oscillator. A little quicker now that we've kind of had the idea in our head from a pendulum. It's very similar here. But ask yourself about your predictions you made before about, remember there was K, spring constant, mass, and then displacement. For this one, it's kind of the opposite. It's actually K and M that matter here. And distance from equilibrium does not matter, actually. Kind of for the same reason as a pendulum, as the angle Y doesn't matter. Because if we have a spring oscillator, right, and we stretch it out, and say this is the equilibrium position here. We stretch it all the way out to here. As the distance gets larger, so does the force, right? Because remember, Hooke's law says that force of a spring is equal to kx. So as x increases, so does the force. If the force increases, so does the acceleration. So the restorative force for a spring oscillator is the spring force, right? It's the same thing in this case. So if I stretch it out all the way maybe to here, then the restorative force will be even larger, which means that the acceleration will be larger, which means that it's going to, spring back really fast, and so the distance actually doesn't matter. So for a period, so the restorative force on a spring oscillator is the spring force for horizontal spring. Let's look at a hanging spring real quick. Sometimes you get problems with our hanging springs like this from a ceiling, vertical springs. Now, if we stretch the spring down this way, and imagine this in your head, right? I have a spring hanging down, I stretch it down like this. Which force is going to make it go back towards equilibrium? The spring force, right? Okay, makes sense. But what if we squeeze the spring up? What if we squish the spring towards the ceiling, right? What if you take your hand, you push it up? Well, then you're actually going to have two restoring forces. You're going to have the weight force, so that's still down, right, towards equilibrium. But the spring force is also pushing down. So in that case, you actually have two restorative forces. You have the spring force and the weight force both pushing down toward equilibrium. Whereas if say equilibrium is here, all right, in the first case with this guy, spring force is up and weight is down. So weight force is not restorative because it's not in the direction of equilibrium, but the spring force is. So in this first case, spring force is restorative. In the second case, both forces are restorative. All right, kind of a not super important detail, but there you go. All right, so what about the period? The period of a spring oscillator is very similar formula as before, but it's slightly different. So for a spring oscillator, period T, put a little S there for spring oscillator. So it's different from the P for pendulum, right? Equals, again, 2 pi square root, but this time instead of L over G, it's going to be M over K, because those are the things that matter for a spring oscillator. Read the K a little better there. Right? I mean, that's little k, not big K. Little k, the spring constant of the spring, and then M, the mass of the object attached to the spring. All right, so there you go. So real quick problem maybe we'll do, we got a spring oscillator here. Spring constant is, let's say it's, 100. And we got a spring here. Its mass is, I don't know, say 500 grams. And we stretch it a distance from equilibrium. So equilibrium position is here. We stretch it a distance, 75 centimeters. What is the period of the spring mass oscillator? In other words, how long will it take for it to go down and then back one time? Well, period of a spring oscillator is 2 pi. Square root of the mass, make sure it's in kilograms, so 500 grams is half a kilogram, so 0.5 over K, spring constant, is 100 in this case. Distance doesn't matter how far away from the equilibrium we go. It's all not going to make a difference here, so we'll do the math. So period of spring here will be 2 pi times, 0.5 over 100 is 0.005, square root of that. It's a very small number, 0.07. So that's going to be 0.07 times 2 pi is 0.44. So a little less than half a second for that spring oscillator to make one complete cycle. All right, there you go. So that's the formula we're going to be using for periods of springs and pendulums. And while you might get 1 or 2 questions about actually doing calculations, usually most of the time the kind of questions we're going to get is about the relationships between these things. So we'll do some practice about that in a second. But now you know the formulas. Let's talk about energy. All right, energy in a pendulum. Very quick, guys. I don't make this video too much longer because we're already kind of going long, and I know y'all are probably ready for this to be over. All right, so for pendulum, equilibrium position is here. We're going to call this position the 0 height, right? We're going to call this our origin height. So this is height equals 0 at that equilibrium position. If we raise the pendulum up, say to here, this position, right, we have gained gravitational potential energy, right? We have gained UG, which of course is mgh. And as this object falls, of course, it's going to lose mgh. So at its lowest point, it's k. At its, let's call this position 1, and let's call this position 2. At position 1, the k, let's not circle it, at position 1 will equal the gravitational potential energy at position 2, right? Because that energy transforms into kinetic energy. So we would say that 1/2 mv squared at position 1 equals our mgh at position 2. They must be the same. You can use this information to solve all kinds of different problems that you might get, like how fast is the pendulum going at the bottom and stuff like that. You'll notice that both things have an m in them, so m's will cancel. You know what g is, 10, right, if we're on Earth. And then the height you can figure out. It'll usually tell you, it'll give you part of the problem usually. And then you can find v, or if you know what v is, you know how high you were, and that sort of thing. All right. So keep that in mind. I'm not going to go into more detail on that right now. It's pretty basic. We've done stuff like this before. It isn't new. I know it's been a while because you've been on spring break for like 2 weeks, but you know this stuff. It's in the back of your mind somewhere. We've done like this before. For a spring oscillator, very similar. A little bit more confusing for springs just because students get a little confused about where the object has zero potential and zero kinetic. So we have a spring oscillator here. So this is our equilibrium position right here down the middle of the object. So if I have the object stretched out all the way to here, let's call this position 1. This is position 2, and I have another one where it's squished. So this is equilibrium here, and object here. So I have 3 different positions, right? All the same spring oscillator. It's just initially position 1. I'm going to stretch it out to position 2. I'll let go. It's going to go whoosh, compress the spring to position 3, and then it's going to bounce back out, and it's going to oscillate like that back and forth, right? Well, we know that at position 2, we're holding the spring there, right? We have it physically in our hand. It's not moving. So what kind of energy does it have? Well, it has spring potential energy, right? And we remember that spring potential is US 1/2 little k x squared, where k is a spring constant and x is the position of the object from equilibrium position, right? As the object goes back towards position 1, right? The energy at position 1, it doesn't have any spring potential energy because it's at equilibrium position. So the x is 0, but it is moving now. And so our k at position 1 must equal our spring potential from position 2, right? It must be the case. Same thing is true at position 3, or similar thing. The k at 2 must equal our spring potential at 3. And we can also say that the spring potential at 3 must also equal the spring potential at 2, right? It's just going back into the spring, right? And then back to kinetic, and then back to spring, and then back and forth. Remember, ask yourself, where is the spring moving the most, and where is it not moving? And you know it's not moving at the ends, right? Because it slows down, stops, and then accelerates back towards the center. And then on this end, it slows down, stops, and accelerates back towards the center. So at the end, it's not moving, which means all the energy must be spring potential. But in the middle, it's moving the fastest, so the energy is kinetic. And you can use that information to help you find, whatever a problem might be asking you for, whether it's, a spring constant with a velocity or whatever it might be. Okay. All right. Cool. So that's about energy. I'm not going to go into more details on that right now. You guys will do practice problems in the book, and we'll figure it out. Again, similar stuff you've seen this before. It's not new. It shouldn't be too crazy of an idea. All right, cool. I'm going to do some little example problems, little quickies from the book to kind of help you flush out any misunderstandings you might have. Hopefully kind of, wrap a bow on this, and then we'll wrap it up, all right? All right, so let's do some little practice problems. Most of these are about the relationship between the different quantities, but I think it'll help you kind of figure this up, kind of wrap up this quick little unit. And again, it's not, I'll be honest, it's not the most important unit. It's probably 10%, 5% of the AP exam. So, but you know, that's points you want to earn. So let's take a look at some of these problems. All right. First one, a mass oscillates on a horizontal spring with a period of 2 seconds. What is the frequency? Well, we have to recall. And of course, by the way, on all these problems, I want you to pause like right now, try the problem on your own real quick, get an answer, and then unpause and then check and see if you're right or not, right? That should be kind of that should be go without saying, but I'll say it anyway. All right, we know that period, capital T, equals 1 over frequency. Well, if period is 2, we also know that frequency is 1 over period. Well, period is 2, so that means frequency is 1 over 2, which is all the way known as 0.5 or a half, right? So half a hertz. All right, so in other words, remember, very important to remember the difference between period and frequency. Period is how long it takes to complete one cycle. It's saying that this little mass here is going to go down and back, and that whole process takes 2 whole seconds. So how many cycles does it make in 1 second? Well, only half a cycle, right? Because it takes 2 seconds to do one. All right, so that's a pretty easy one to start off with. Let's go to the next one. All right, so again, read the question, pause the video before I give the answer, check your work. A typical earthquake produces vertical oscillations of the earth. Suppose a particular quake oscillates the ground at a frequency of 0.15 hertz. As the earth moves up and down, what time elapses between the highest point of motion and the lowest point of motion? All right, so pause, do your work, check it. Okay, now you're back. All right, highest point and lowest point. Highest point, lowest point. So how long does it take the earth to go from here to the lowest point? Right? What time elapses between the highest and lowest point? Does not say how long to go down and back, only to go to highest to lowest. You gotta be careful with little details like this, right? Because it will get you. How long does it take to go from the highest to the lowest, but not back? So we're not completing a whole cycle here, okay? Now we know that the period is 1 over the frequency. Well, it gives us a frequency of 0.15, so that means period is 1 over 0.15, which is 6.67. However, it is not asking for the period. Period would be down and back. This is not asking for that. It's only asking for how long it takes to go from the highest to the lowest point. Well, that's going to be half the period, right? Instead of down and back, it's just down, and then that's it. So what's half of 6.67? Well, it's going to be 3.33, which is our answer. All right, so there you go. Hope that makes sense. All right, next one, a block oscillates on a vertical spring. When the block is at its lowest point of the oscillation, its acceleration A, and then the Y for the vertical plane, is in which direction? Is it negative, in other words down? Is there 0 acceleration, or is it acceleration positive? All right, so pause, check your, get an answer. Now you're back. What direction is the acceleration? A lot of students say 0 here. It's not 0. The answer is, getting my pen, positive. The acceleration is positive. Think about what the block is about to do, right? A block accelerates a vertical spring. When the block is at its lowest point of the oscillation, so you get a spring, bounce it up and down, right? Bounce up and down like this. At its lowest point, it stops for an instant. Remember, just because an object is stopped, does that mean it has no acceleration? No. It can have no velocity, but it's still accelerating. The same way we take an object, right? I throw an object in the air, it goes up, stops for an instant, and then it falls back down, right? But is the acceleration 0 at its peak? No. If it was, what would the object do? It throw it up in the air, slows down, stops. If the acceleration was 0, the object would just sit there and float. It wouldn't move at all. That's weird, right? It doesn't work that way. We know the ball falls back down. Same thing here, right? We know that spring at its lowest point, it's going to move back up. It's got to get pulled back up by the spring force. Well, with the spring force pulling it up, which means its restorative force is up, which means the acceleration is also up. It's going to go back up, so positive force. All right. So this next one is a little tricky. It's the first one that kind of might throw you for a loop here. So let's see. 2 identical blocks oscillate on different horizontal springs. Which spring has the larger spring constant? Red spring, blue spring, or can't tell. All right. Let's see. First thing we got to do is remember that we know that the equation for the period of a spring is T, and then for a spring S is 2 pi times the square root of m over k. We also know that the frequency for a spring then is 1 over 2 pi times the square root of k over m. Where little k is a spring constant, right? So that's what we're looking for here. Now, the question is, how does a graph help us, right? What do we do with the graph so that we can tell what the answer is? All right, well, I think it helps in this case to kind of think about what these positions mean, right? So let's do the blue one first. Let's look at that. So we got a position here is important, here, and here. I'm going to call this position 1, 2, and 3. Now, if we look at this like an actual spring, let's say this is equilibrium here. That means when the spring is out here, it's position 1, when the spring gets stretched out, this is 2 at equilibrium, and this is 3 when it kind of compresses, right? When it has negative displacement from equilibrium, okay? So 1 far away from equilibrium, 2 at equilibrium, and then 3 we've compressed the spring, squished it, and now it's, on the other side of equilibrium, all right? Well, what is this telling us here? If we go from 1 to 2 to 3 and then take back to here and back to here, isn't then this one whole cycle, right? So isn't the time, like the x-axis is time here, so isn't from here to about here, that length there, isn't that capital T, or one whole period? Which means that the same thing for the red one then, right? From here to here, this is our T for the red one. So which one has a larger T? The blue one, right? The blue spring has a larger T. If it has a larger T, that means F should be lower, right? Remember, they're inverse. T equals 1 over F, and F is 1 over T, capital T. So they're inverse of each other. If we have a large period, we have a low frequency. We have a high frequency, low period, and vice versa, right? Okay, well then, let's look at the relationship between frequency and spring constant K. Which one of these objects has a larger spring constant? A larger frequency, excuse me. Got ahead of myself. Well, the red spring has a smaller period, and if T goes down, that means frequency must go up, right? If frequency goes up, look at the relationship between K and F. They're both in the numerator, right? M isn't changing. 1 over 2 pi is a constant. That doesn't affect anything. K is in the numerator, so is the frequency. So if frequency goes up, as it is for the red spring, so will the K, right? And that's what's happening. So the answer is red spring, all right? It's a tricky one. Hopefully that makes sense. Remember, guys, I'll just kind of interject this real quick at this point. If you have questions over anything in this video, or from the bookwork I'm going to assign to you, or anything else, like message me anytime, day or night. I'm sitting at home, basically binging shows and playing video games and waiting for you all to message me to help you with stuff, because I am bored out of my mind. Sitting here in quarantine, not a lot to do. So message me anytime. I'm here to help. All right, do a couple more. 14.8. A block of mass M oscillates on a horizontal spring in the period of 2 seconds. If a second identical block is glued to the top of the first block, the new period will be what? All right, this is kind of a tricky one. This is about the relationship here, right? We don't know what the mass is, so we can't plug it into the formula and see. We know the period of a spring oscillating system is 2 pi square root of m over k. And it is, I always get m and k's mixed up. Yeah, m over k. So I gotta check. All right, well, we don't know what m is. We know period is 2 in the original scenario. We're going to double m. Right, now, if k doesn't change and the 2 pi doesn't change, it's a constant, right? The only thing that's changing is the mass. We're doubling the mass. So what's the factor of change for the mass? You might say, oh, isn't it 2 because we're doubling the mass? Well, no, because it's under a radical, right? So if we double the mass, that's a factor of 2, But then what's the square root of that? Because m is under a radical. So the square root of 2 is about 1.4. I will double check, but yeah, about 1.4. So that means that our period is going to change by a factor of 1.4. And where did I get that number from? Again, square root of 2, right? Because we're doubling the mass. Right? We got one block. We're going to glue another block, an identical block, on top of it. So we've doubled the mass. So it's 2 times the mass, but it's under a square root sign. So square root of 2, 1.4. So our factor change of 1.4. What do we do with that? Well, remember, take the factor change, multiply that by what the original amount was. Well, the original amount was 2. So what is 2 times that? And we get 2.8. The answer is, well, if we double the mass, we're going to have now our oscillation be 2.8 seconds. And I got that from the square root of 2 times 2. All right, hopefully that process makes sense. If it doesn't, send me a message, hit me up, and we'll chat about it. We could even, well, I'll talk about this later. All right, I was going to say we can do like a Google Meets thing and kind of go face-to-face if you want to, but I'll mention that some of this in the Schoology. All right, a couple more of these. All right, next one. A mass oscillates on a horizontal spring with period of t equals 2 seconds. If the amplitude of the oscillation is doubled, the new period will be what? Amplitude refers to how far we pull the spring away from equilibrium, right? So this is our current, let's say equilibrium position is, let's say it's here, okay? So we stretch the spring out to here. If we stretch it out even further, now if I stretch it out all the way out to here and have the mat, you can't even see that, I think my head's in the way. Oh no, it's not. Stretch it all the way out to there. Now what will the period be? All right. Well, remember, period of a spring oscillator, 2 pi square root of m over k. I don't see amplitude or displacement anywhere in here because it doesn't matter. If the period was 2 before, guess what it is now? It's still 2 because changing the distance from equilibrium doesn't make a difference. Answer is the same as before. All right. All right. A series of pendulums with different length strings and different masses is shown below. Each pendulum is pulled to the side by the same small angle. The pendulums are released and they begin to swing from side to side. Oh, the picture's in the way. Let me move it out of the way so you can see the... I'll make it smaller. That's good. That'll work. Which of the pendulums oscillates with the highest frequency? Highest frequency. All right, well, we know. Now we have a pendulum here. Period is 2 pi square root of L over G. But it's acting for frequency. So frequency then is the opposite of that. Flip it over. 1 over 2 pi and square root of G over L. All right, well, look at this now. No math here, right? It's about the relationships. G is the same for all of them, right? The masses don't matter. The mass on the pendulum doesn't make any difference on how long it takes to go back and forth or any of that stuff, right? Doesn't matter. G is the same for all these things. They're all on Earth, we're assuming, right? So G is the same, but the L is different. The lengths of the string are different. So which one had the highest frequency? Well, if L goes down, it's in the denominator, right? And frequency in the numerator. Look at this equation right here. L is down here in the denominator. And I know it's in a radical, but don't worry about that for the moment. It's in the denominator. Frequency is in the numerator. That means we have an inverse root relationship. In other words, if L goes down, frequency will go up, right? Well, only one of these strings has a shorter length, and that's A. And the answer is A, right? Smaller L means greater frequency F, right? B, C, and D all have the same length of string, even though it sure looks like C is longer, but it says 15 here, but it sure looks like it's longer, but whatever. I think they did a typo probably there. Probably meant to say 20 here, but it doesn't matter because the answer is A, because small L means big frequency, right? Thanks to our equation, we see that relationship. All right, last one. This is gonna be it. Promise. Last question. All right, we have a mass on the end of a string is pulled to the side and released, and so we have these different instances, right? So we have position A, position B, C, going the other direction, D, and then E. We had 3 questions in this one. At which time or times shown is the acceleration 0? At which time or times is the acceleration 0? So I'm going to pause it real quick, answer these, come back. All right, now you're back. Where is the acceleration 0? If the acceleration be 0, what else must be 0? Net force. Where is the only position or positions where the net force will be 0? That's at position B and D. At B and D, the only force on the object is tension up and weight down, and they're going to cancel out, right? They're going to be, they're going to be opposite but equal, cancel each other out, so the net force is 0, which means the acceleration is also 0 at B, and same thing at D. All right? What about the next one? At which time or time shown is the kinetic energy at a maximum? At kinetic energy at a maximum. All right. Pause it. Answer. Now you're back. All right. Well, we know at A and C and E, that's where the object was when it was released, right? In other words, it goes up, slows down, stops, and then moves again. So we already went over this, right, with the energy stuff. Where is the kinetic energy at a maximum? And that's at B and D again. At the bottom, we have no potential. All the energies in kinetics, moving the fastest at the bottom, and has no potential at the bottom. But all kinetic energy there. All right, last one, part number 3 there. At which time or times shown is the potential energy at a maximum? Well, it should be obvious. If the kinetic energy is at a maximum at B and D, then the potential energy will be at a maximum at the other positions, A, C, and D. Right, they're at the highest points, and so they have the most height from the equilibrium position, height-wise, vertical distance, and so they're going to have the most potential energy at those spots. All right, hope that kind of makes sense. That is a quick and dirty of harmonic motion. If you have any questions over the video, the bookwork, the FRQs that have been assigned to you, please do not hesitate to message me. I'll be waiting around, on the edge of my seat, waiting for messages because I am bored out of my mind, as many of you probably are also. But at least you got something to do now, right? Silver lining here, okay? So go through the notes, see if it makes sense, do the bookwork, FRQs by the end of the week, and we'll start reviewing next week for our AP exams. As of the recording of this video, I still don't know what the dates will be of the AP exam, but as I said in the remind message, it will be only FRQ. So we're going to do a bunch of practice FRQs over what we learned so far throughout the year. So, hey, hope you're all doing well, washing your hands, staying safe, not getting sick. I know you guys are all young, and you probably wouldn't get sick, but you don't want to spread it to other people who might be susceptible to the disease. So, stay in if you can, do all that stuff you're supposed to do. You know the drill. Hope you're surviving and not going too bored or dying of boredom. And that's all I got. All right, so guys, hope I can see you again sometime soon. Even though I haven't seen you in a couple weeks, you're still in my life. I don't have much of a life. I'm here at home waiting for you. Ask for help. So I'll see you when I see you, hopefully soon. Bye, guys. Have a great one. Adios.